Partial derivatives occur, of course, when we're working with functions of more than one variable, such as the height as a function of position in two directions. We talked about north-south and east-west, so north-south perhaps like this and east-west like that. However, we could just as well have chosen two other directions at right angles to one another, maybe from the southwest to the northeast and the southeast to the northwest. Those can still be at right angles, but they're not the ones we had before. So when working with such functions of more than one variable, we're going to have to deal with the idea of changing from one coordinate system to another. If, for example, we know the slope of some hill when we're going in the north-south direction and the east-west directions, can we therefore work out what it is in our new coordinate system when we're going southwest to northeast and southeast to northwest? We can do this, and manipulations like this are quite important, mostly because a new coordinate system will often turn out to be much more convenient for the problem we would like to solve. Now, a very good example of a different coordinate system is what we might think of as spherical coordinates, where we express the position of some point in terms of a radius and two angles. So, for example, a polar angle relative to a north pole, as it were, sticking up here, and another angle in the plane. Those three coordinates, that angle, this angle, and the radius out along that, would be good coordinates, but they're not x, y, z coordinates. Now, those spherical coordinates themselves, we'll deal with the details of those later, but we should understand in general the principles of how we can handle derivatives as we change from one way of expressing our coordinates and our derivatives to another way. To start this, we will need to look at the idea of differentials. And that idea is also going to help us with another idea along the way, which is what we call the total derivative. So let's look at one patch of a function, our same function f of x and y, but we're just looking at one small patch of it. So this patch is delta x long in the x direction, delta y long in the y direction. Our question is, how much does the height change, this height delta f is the change in the height, as we move from one corner up to the other corner? So as we move by delta x along the x direction, the height changes by the amount of this red line here, and that length of that line is partial df by dx at constant y, that's the gradient of this line here, the slope of that, times delta x. And so we've accumulated this much change in height, delta f. And then as we move by a distance delta y along the y direction, the height changes by this additional amount, this red line here, and that amount is the slope of this line times the amount delta y. So this is the gradient partial df by dy at constant x. And so we take this bit of red line and add it on over here. So now we've figured out the total change, delta f, in the height of this function as we went from one corner up to the other. So, writing this out explicitly, this amount delta f is this piece of red line, which is this much, plus this piece of red line, which is this much, to get the total here. So in the limit, as we make the delta x and the delta y very small, that is, as we make them what we say is infinitesimal, this entity here turns into this one. And this is called a differential, or sometimes an exact differential. Suppose now that we're out for a walk on a hill. It's a nice sunny day, and we're walking along a path, and we know the direction that the path is going on the map. And perhaps we know the slope of the hill in a couple of directions. But the path might not be along those directions. It might be along another direction. can we find out how fast we are gaining height based on our understanding of the slopes of the hill in a couple of directions, even though our path is going off in another direction? To understand how fast we are gaining height, we need to look at something called the total derivative. We suppose that we know the slopes of the hill in the two coordinate directions, so df by dx at constant y and df by dy at constant x. We presume also that we know how fast we are moving in the x direction and in the y direction. So that is, we know the two components of our velocity. So in the x direction, our component of velocity in the x direction is dx by dt. And note that this is an ordinary derivative here. We're not holding anything constant. We're just saying how fast are we going in the x direction? What's our velocity in the x direction? And similarly, what's our velocity in the y direction, or what's our component of velocity in the y direction? And that also is just a conventional, simple, ordinary derivative. So in some small amount of time, delta t, we will have moved amounts delta x and delta y in the x and y directions. So the amount we will have moved in the x direction, the delta x, will be our velocity component in the x direction, times this amount of time, delta t. And similarly, the amount that we will have moved in the y direction, delta y, will be our velocity in the y direction, dy by dt, times delta t. So, using our differential idea, we're going to substitute in for the delta x and the delta y what we know from our velocities and the amount of time that has passed. So, our delta x was our velocity in the x direction times delta t, and our delta y was our velocity in the y direction times delta t. Or equivalently, we could divide out by the delta t's, so delta f over delta t is given by partial df by dx at constant y times dx by dt plus partial df by dy at constant x times dy by dt. Or in the limit of small delta t, we have this total derivative, df by dt is the gradient in the x direction at constant y times the velocity in the x direction plus the gradient in the y direction at constant x times the velocity in the y direction. And note that this is a conventional derivative here. It's not a partial derivative. We're not holding anything constant. We're just saying how fast are we gaining height. And that gain in height is made up out of some amount from our movement along the x direction plus some amount from our movement along the y direction. So this could be called a total derivative in contrast to a partial derivative. And see that it's made up out of two parts using these two partial derivatives. Now we're going to make another use of our differential, this time to understand how we change the coordinates for partial derivatives. Suppose we want to know the slopes of a hill, or hill f of x and y, but not along the x and y directions, but along another couple of directions. So not along east and north directions here, the x and y directions, but along the southeast direction and along the northeast direction. But we only know the slopes along the east direction and the north direction. That is, these two slopes, partial df by dx at constant y and partial df by dy at constant x. Well, we do know that if we move southeast, that is along the direction A here, by 1 unit, so this fuzzy green line is 1 unit long, then we move east by 1 over root 2 units, because 1 over root 2 is the cosine of 45 degrees. So moving 1 unit along here in the southeast direction means we move 1 over root 2 units along the east direction, because 1 over root 2 is the cosine of 45 degrees. So in other words, the rate of change of x with a at constant b is in this case 1 over root 2. That's how much this changed as we moved along this line by a unit amount. Similarly, the amount that y changed as we move along the green line here by 1 unit, in this case y actually decreases, and we really have minus 1 over root 2 here, movement along the y direction for 1 unit of movement along the positive a direction. So partial dy by dA at constant b, in this case, is minus 1 over root 2. Similarly, if we were to move along the b direction by 1 unit, then we would move along the positive x direction by 1 over root 2 units. And that 1 over root 2 is dx by db, partial derivative, at constant a, because we're only moving along the b direction. And that also, in this case, would be 1 over root 2. Similarly, if we ask how much y changes as we move along the b direction here by 1 unit, the answer to that is 1 over root 2. dy by db at constant a is 1 over root 2. Suppose that we make a small movement, delta a then, along this southeast direction, and no movement at all in the northeast direction. Then we will move an amount delta x along the x-axis, that is dx by dA at constant b times delta a. And in this case, that would be 1 over root 2 times delta a. Similarly, the amount that we have moved in the y direction by moving a small amount, delta a, along the southeast direction here, the a direction, is partial dy by dA at constant b times delta a. And in this case, that's minus 1 over root 2 times delta a. So with these results, that delta x can be written as partial dx by dA at constant b times delta a, and similarly, delta y can be written as partial dy by dA at constant b times delta a. The resulting change in delta f, in the value of the function f, from this movement along the a, or the southeast direction, is delta f is equal to partial df by dx at constant y times our delta x here, which is partial dx by dA at constant b, times delta a. And similarly for our movement along the y direction here, that's our delta y as a result of our delta a. So we multiply that by partial df by dy at constant x. So therefore, starting from this expression we just figured out, dividing both sides by delta a, we obtain this expression here, and taking the limit of small delta a, and noting that this time this is all done at constant b. Notice these partial derivatives are at constant b. So this change delta f with change delta a is all done at constant b. Then we have the partial derivative, partial df by dA at constant b is given by all this expression here. So given that we knew these gradients, partial df by dx at constant y and partial df by dy at constant x, we can figure out the gradient along the a direction at constant b, partial df by dA at constant b. What we have to know are these two partial derivatives, partial dx by dA at constant b and partial dy by dA at constant b. So now we've achieved what we wanted to do. We knew these gradients and we wanted to figure out this one. Now, since this is just a number, partial dx by dA at constant b for some specific value of b is just a number, and similarly this is just a number, we can move these around here, and what we're going to do is we're going to swap the order of these two. to get just another way of writing the same thing as up here, but you'll see why we're doing that in just a minute. So I've just swapped the order of these. Swap the order of these. Since this expression holds for some arbitrary function here, we didn't specify what it was other than that it has appropriate derivatives. Since this is true for any function f, we can write more generally partial d by dA at constant b is equal to partial dx by dA at constant b times partial d by dx at constant y plus partial dy by dA at constant b times partial d by dy at constant x, where we understand this is operating in any function. And I understand that this notation gets very confusing, but you can see how we've built it up here. And this is the general way of changing coordinates for a partial derivative.